Thank you for reminding me. Yeah, I just got a letter from the Dallas police saying that I owe them money because of a ticket I got for letting my car stay too long at the next to the college without money in the meter. Yeah, they weren't happy about it. So in this chapter, we're talking about multiple integrals. For each derivative that we were able to take in the past with one variable, two variables, three variables, an infinite number of variables, we can also find the integrals, which is going backwards. So we find areas in calculus 1 under the curve. We have one single variable. Two variables, we find volumes now, because we have width, depth, and height. And then triple integrals find us volumes under a region in space. All right, so in the first section, we're dealing with double iterated integrals. Over rectangles. Again, this is just a continuation from calculus 1, really. Because what we have to deal with here, same as in Cal 1, that we're going to look at definite integrals for continuous functions over a closed interval. As in calculus 1, we will use the Riemann sums. To calculate the areas and volumes of these rectangles. Okay, let's recap what we did in Cal 1. In Cal 1, we said that y is equal to f of x. So it could be any curve. On a closed interval, so we're looking for the area under the curve between A and B. The way we did it was we made rectangles. All the way equal size rectangles of all these spaces under the curve. The only thing that was variated was the y values. So as our delta x, as the width of these rectangles went to 0, the number of these rectangles, so the areas of these rectangles, so as delta x goes to 0, the area reached its limit. And then we got an accurate representation, or actually, to be honest with you, so it's more like as an approximation of the area under that curve. So we're going to do the same thing now in this chapter, in Cal 3. We're saying that z is equal function with two variables. So we still have our x and y components, but now we have the z-axis. So we're going to do the same thing here. We have our delta x. We're going to separate each one of those. So let's say our curve looks like this. But as we have each of our delta x's, we also will have to have now delta y's. So what's going to happen here is where they intersect are these little squares. As we go up higher, we now have this rectangular column. And that's what we're going to have to find the volume. We have to find the volume of each one of these columns and sum them all up, which is what the Riemann sum is all about. And then the smaller we make the delta x, delta y, the more accurate we're going to have. So the smaller we make those, the number of rectangular columns goes to infinity. All right, so what's going to happen here is in our function, we have a region that we have to look at, and the region has two domains that we have to abide by. The horizontal region, we're going to be from A to B, and then our y component, we'll go from C to D, and those will correspond to our rectangular regions. Each one of these are called partitions. We're making each section smaller and smaller and smaller and smaller and smaller. And if you call it mathematically, the Riemann sum the summation of each one of our however many rectangles we have, however many delta x, delta y's we have. We have our x and y component, which is the area of that curve, of that box under there, times the function times the area of that curve, of that box. So here we have the area times the height, which will equal the volume. So the more of these boxes we have, the more accurate our estimation of the true volume of that object becomes. Now, we have another terminology here. We're going to use something called the norm. It's represented as that, where P represents the height and width of the rectangle we're looking at. What this says, whenever we use a norm, we use the largest value of height and or width, whichever is larger, of any of the rectangles. This allows us to keep our calculations more uniform. Because if not, then these delta x, delta y's can vary depending on where you're looking at. So this is we use the norms to parametrize everything so it's all in the same dimensions. So because the norms now dictate the size of our width and height, our sums are now affected. As our p-value we choose smaller, smaller, smaller. As it goes to 0, the norm goes to 0. So therefore, our limit of our summation function as our norm approaches 0, that's our approximation of the area, of the volume, I mean. So as our norm goes to 0, then the delta area of each of these goes to 0 because they get smaller, 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 smaller. What that means is the number of them that we have. So the number of these rectangles that we have, the smaller we make them, the more we're going to have. So as our norm goes to 0 is a result of results in the number of these partitions going to infinity, which will give us this. Times so again, the whole thing is the smaller we can choose our delta sizes, the more calculations we're going to have, but the more accurate our calculations will become. All right. So if these exist, we say that the function, no matter how many variables it has, is integrable. Integrable. And the limit is called the double integral of f over r. So if all of this stuff exists, then we say it's integrable, and the limit is called the double integral of f. So in other words, it looks like this. It's over the region of our function xy times the change in area. Remember, the area was delta A. Remember, the region was limited by our values for x and y, which are bounded by x is bounded by a and b, y is bounded by c and d. So this becomes our double integral dx dy. Because we have to worry about, okay, our area is made up of height and width, which is the x and y. Well, how do we integrate them? So we integrate them, and we're going to find out in an example that as when we did the double integrals, the partial of fxy is the same as the partial of x fyx. Same with the integrals. This is the same as f of xy of dy dx. So the order of integration is irrelevant. It'll give us, because we're looking for the area under the curve. The area is not going to change depending on how we take it. All right, so that's what we're going to look at. So we're going to do integration with x and y first, and conversely do the other integration with the other variable. All right, let's look at double integrals as volumes. Whenever we find the double integral of our function in whichever order we choose to do it, it's going to be over a rectangular region in the xy plane. We find that the value that we get represents or is the volume of a three-dimensional object over the xy plane. Of course, it's bounded by R. So it's bounded by the domain of R and the range of R, and is the surface, or the, I don't want to use upper bound because that's a whole nother, is the bound above the xy plane. So by doing all this stuff, what's happening here is, again, we get our x and y components. We find the shape of the object first. Let's say it's a circle. And then on the z-axis, it gives us a height, up and down, whatever. So that gives us now a cylinder. And we could use these properties here to find the volume of the cylinder. Again, it's looking at the xy plane, so we find the area and then the volume by knowing the height, the delta A. So the volume of an object is determined by the limit of all these little rectangles, which is calculated by that. Where the delta A goes to 0 as n goes to infinity, as we talked about earlier. As n goes to infinity, this the delta A, the volume of these columns goes to 0 because they become infinitely small. So the more of these objects that we have, as in the more of these rectangles that we have, or these columns that we have, and the smaller they are, the better it is to find the volume. Fubini's theorem for calculating double integrals. Guido Fubini, not Dini, Fubini, Italian mathematician, late 1800s, early 1900s, who came up with this. And again, the biggest thing here is going to be the proof that it doesn't matter how you integrate them, it'll get you the same answer. So as the book says, is suppose you want to find the volume under the plane z is equal to 4 minus x minus y. Over the rectangular region R that defines the bounds of our x and y as these in the xy plane. So again, we're only looking at rectangular regions because we want squares or rectangles. Because you can use whatever shape you want to, it's just that these are much easier to calculate. Using the slicing method, of partitioning, with perpendicular slices to the x-axis, we get the volume as being, remember, with respect to the x, it goes from 0 to 2. We have the area of the object, dx. But remember, this is the cross-section of perpendicular with respect to the x-axis. So wherever our shape is, we're only looking at it's perpendicular, so it'll project up to here, and we're looking at that area. right?
Could you explain that graph again?
Okay, yeah, what we're looking at here is we have the shape of our object in three-dimensional space. Since we're slicing it perpendicular to the x-axis. So what we're looking for here is the area of each of these rectangles that are perpendicular to the x-axis. So each point here is only an x value, but we go for the y values, we go from, in this case, from 0 to 1. So it's 0 to 1 wide and f of x high, but we have this many of them. So our delta x is going to be how wide our rectangles are going to be. Because remember, we're looking for the volume. So we have to find the area under the curve first of each of these rectangles and then add them all up. That'll give us the volume. Okay, so since we're perpendicular to the x-axis, we have this formula. But what is a of x? The area of x, now it's dependent on the y values. So here we're going to look at the formula itself, the 4 minus x minus y with respect to the y value. So actually, does that answer your question about what that picture represents?
Yeah, it does. Wait, all the squiggly lines, is that just showing like the 3D aspect of it?
Yes. Actually, I wish I had multicolored pens. That would have made it much easier. Let me see if this would help. Because here is our curve. And we pick a location for x with our delta x size. And then we know the y goes from 0 to 1. So this gives us the area of this rectangle. And then we multiply it by the height and we get the volume of that cube, or that slab. So we first define the area, the function with area of this times each of these x's from 0 to 2. Now we have to define what a of x is. A of x is the function with respect to y from 0 to 1. So when we take the integral of this one with respect to y, we get the integral of 4 is 4y minus the integral of x with respect to y is xy. And the integral of y with respect to y is y squared over 2. The way you test it is if you take the derivative of 4y has to equal 4. If you take the derivative of xy has to equal x. So this is the function, this is the derivative of that function. Starting from the top one, we have 4 times 1 minus x times 1 minus 1 squared over 2 minus y is 0, so those are all 0. So our new function we have to look at, which is 8 over 2, so it's 7 over 2 minus x. That's what a of x equals. So now we take that, plug it into here. 7/2 minus x dx from 0 to 2. Integral of 7/2 with respect to x is 7/2x minus integral of x is x squared over 2 from 0 to 2. 7/2 times 2 minus 2 squared over 2. It's x at 0 is 0. So we get 7 squared is 4 2 minus 2 is 5. So the volume under that region, the plane z equals 4 minus x minus y, in those regions is 5 whatever units. So with this one, we notice we first had to find the area. So we did the y value first. We took the integral with respect to y. And then from there, we did the integral with respect to x. What that would look like if we put them both together. So we first did with respect from 0 to 1, we did the area of the curve dy. And then the second integral, we went from 0 to 2, we did it with respect to x. So what Fubini told us is when we do multiple integrals, start from the inside, work your way out. Right? So, now, these are called iterated. Iteration simply means a repeated pattern. In other words, repeated integrals. We had to first take the integral with respect to y, then we took it with respect to x, and that found our volume. So let's look at if we reverse the process. What if we took the slices perpendicular to the y-axis, in other words, with our graph being the same, we have our curve. Now we are perpendicular to the y-axis. So now we're looking under this area of the curve. We're just slicing it perpendicular to the y-axis now. So that means we have to find the area with respect to the y-axis. And the y ranges from 0 to 1. So we have to redefine, this is with y. So now we have to redefine what the area is. The area is from 0 to 2. 4 minus x minus y. Now we're going to take it with respect to x. So we have to first integrate 4 minus x minus y. So we get 4x minus x squared over 2 minus yx, because we're taking it with respect to x. So we first take it at 2. 4 times 2 minus 2 squared over 2, 2 times x. Then at 0, they're all 0. Now it's 2y. So we get 8. 4 divided by 2 is 2. X minus 2y. We're taking it with respect to x. So that's x. That's 2y. That's not, it's, yeah. Just becomes 2. Right. So this is now a function of y. We take that with respect. We integrate with respect to y now. We get 6x minus 2y squared over 2. Now we get 6 times 1. Well, the 2's cancel. 1 squared. Then they both have x, so it's minus 0, which is 6 minus 1 equals 5, which is the same thing. So what Fubini found for us was that it didn't matter which order we integrated, we get the same solution.
I have a question.
Yes.
How would 2x squared over 2 become 2?
2 squared over 2? But 2 squared is 4 over 2 is 2.
No, but isn't there x? Is it 2x? Or is it just a 2? Because the 2.
Well, no, it used to be, but wherever I saw an x, I put a 2. But remember, the first one I'm integrating with respect to x. So this is what x becomes. Anywhere I see an x, I put a 2. So that's where it became 2 squared.
Oh, it just looked like there was another x, like right there.
No, yeah, that's right. Yeah, I was I brain fart because I thought that was integrating with y. So no, there was no x there because the x was there, and I replaced the 2, made it 2 squared over 2 is 4. 4 over 2 makes it 2. Yeah. Again, this is you have to be very, very, very careful with this stuff. Like yesterday, one small mistake when you're writing these things, a sign or a number, if you forget to write something, it will ruin the whole day. So be very careful. That's why I always check. I double check whenever I write anything down after I write it. And that's it. The integral of 4 is 4x, x squared over 2, yx. Now anywhere I see an x, since I did it with x, I put a 2. So it should give us 4 times 2 minus 2 squared over 2 minus 2y. And that's where we got that. So let's look at Fubini's theorem. The first form. If we have a function f of xy that is continuous throughout the rectangular region R, where R defines our domains, then our double integrals since AB came first, and that's with x, this first one is dx, and the outer one dy, is the same thing if we did it the other way, if we switched the bounds of integration. Since CD is respect to the y, so that's what Fubini found, is it didn't matter how we integrated it, we get the same answer. That actually, it doesn't sound like much, but it takes a lot of stress out of trying to calculate these things without trying to remember, okay, do I take dx dy or dy dx? It doesn't matter. So it says order of integration is irrelevant. You get the same answer both ways. All right, let's look at some examples here. Calculate the double integral f of x, y, dA for this function, 100 minus 6x squared y, and the domain, the region is x is between 0 and 2, y is between -1 and 1. The only thing we have to be sure, it's not a solid rule. Remember, in differentiation, when we took derivatives, we had to make sure that the function's continuous. Well, we can have integrals of functions that are not continuous, because all we're looking for here is if we have something that's not continuous, then we have multiple bounds of integration. All right, so all we have to do is have function. It helps if it's continuous, because then we just take it one bound. All right, so it's telling us we want this f of x, y dA. Now, originally, so now we worry about, do we take with respect to x or y? It doesn't matter. So I'm going to say from 0 to 2, from -1 to 1. My function is 100 minus 6x squared y. Since I went from -1 to 1, I'm integrating with y first, with respect to y first. And then 0, 2, I'm integrating with respect to x second. So let's integrate with respect to y first. 100y minus 6x squared. Integral of y is y squared over 2. So that simplifies. So we get 100y minus 3x squared y squared from -1 to 1. And then we still have to do the dx one. So we have here 100 times 1 minus 3x squared 1 squared minus 100 times -1 minus 3x squared -1 squared. One squared is 1, so it's 100 times -1 is -100. -1 squared is 1. So we distribute that negative sign. Plus 100 plus 3x squared, which gives us 200. Ooh, the 3x's cancel. So our second part is from 0 to 2 of 200 with respect to x. The integral of 200 with respect to x is 200x from 0 to 2. 200 times 2, 200 times 0. So the volume is 400. Right, let's do one more. Find the volume of the region bounded above by the elliptical paraboloid z equals 10 plus x squared plus 3y squared, and below by the rectangular region 0 to 1, 0 to 2. We're looking for the volume. So since we're looking for the volume, we're looking for that. All right, so let's do x first this time. Our function is 10 plus x squared 3y squared. Since I'm going to 0 to 1, that's dx. Outer one is dy. Let's integrate with respect to x first. So it becomes 10x plus x cubed over 3, 3x y squared from 0 to 1 dy. Since they all have x's, the second part is 0. So we have 10 times 1, 1 cubed over 3, 3 times 1 y squared minus 0. Because all of them have 0, so it all goes 0. 10 plus 1/3, 3y squared. Common denominator is 3, so it's 30 plus 1 is 31 over 3. So that means now we got to take it from 0 to 2. 31 over 3. Y cubed over 3. No. 3y squared. dy. Integral of this one is 31 over 3x, y plus 3y cubed over 3 from 0 to 2. 31 over 3 times 2. The 3's cancel. 2 to the third minus 0. 62 over 3 plus 8. 62 over 3 plus 24 over 3 is 86 over 3. And that's our volume. Right. I'll have these notes and the homework assignment sent out this actually in the next hour or two before my next meeting. Okay, what y'all think? This is not that difficult? All right. Okay, everybody. I will see you all tomorrow. Have a great day.
You have a great day too. Bye.
Bye.